Hello, this is Dr. Brown. In this video that we're recording, we're going to look at test 4 review Zoom video. These will be the things you'll need to understand to do well on test 4. Notice that test 4 will be Thursday and Friday, April 29th, April 30th. And to be prepared, you should have done basically the following here. Watched all the videos in chapter 5, completed all the homework, worked the practice test by yourself, and then if you have difficulty working some of the problems, watch the practice test video. And then you can ask me any questions or even request a Zoom video tutoring session if you need additional help. And of course, you will also have this Zoom video, which we'll be recording. And I will have sent out to everyone all these problems worked in a hard copy for you to refer to. Okay, the first problem we're going to be looking at is using summation notation. The very first one will be this particular summation. We're going to go in and start plugging in k equal 1 through 4, and we'll get 2 cosine of pi plus 2 cosine of pi over 2 plus 2 cosine of pi over 3 plus 2 cosine of pi over 4. Cosine of pi is -1, so this would be -2. Cosine of pi over 2 is 0. This would be 0. Cosine of pi over 3 is 1/2, so this would be +1. And then cosine of pi over 4 would be square root of 2 over 2. So this would be the square root of 2. So the sum would be -1 plus the square root of 2. Now for the second summation, that would be plugging in k equals 0, we get 2. K equal 1, we get 4. K equal 2, we get 6. K equal 3, we get 8. And K equal 4, we get 10. This is 18, 24, 28, 30. So the answer is 30. We'll also need to understand how to calculate the area on the curve using approximations. And there are all kinds of approximations that one could do with very simple geometric figures like rectangles. And for instance, here we have a function, the square root of x, which is graphed here. And if you want to get an overestimate, here we're just simply going to divide it into 4 rectangles. Now, the length of the entire integral is 1, so the delta x, the width of the rectangle will be 1/4. So each of these rectangles is going to have a width of 1/4. And then you want to create a rectangle. And for the last rectangle, we want to have one in just the rectangle just barely is the height that will make the curve be completely underneath the rectangle. So that would give you the height, and you would do the same thing for the next one, and for the next one, and this will be an overestimate. Notice if you did an underestimate, you would take this last rectangle in this particular case and make sure that all of it is exactly is underneath the curve, and do that for the next one, for the next one. And for the last one, the rectangle would be a 0 area. Now, to give you an example of how you would try to get a better estimate, obviously using more rectangles, here is one in which there are 33 rectangles. And the length from A to B is B minus A, of course. And so the width of the rectangle would be B minus A over 33. And so a typical rectangle would have a width of B minus A over 32. And the height of this last rectangle would be basically F of X at 32. So you would sum up all these rectangles, and that would give you a much better estimate than if you just use 4, obviously. Now, the good thing about calculus is we're going to see the fundamental theorem of calculus in a minute that will show us how to calculate exactly the area under the curve if we can calculate the antiderivative of the function. So here we have the first fundamental theorem of calculus, and it says if f is continuous function at every point on the interval a to b, it's a closed interval, and capital F is an antiderivative of lowercase f on a and b, then the integral from a to b of f of x dx, and this would be the area under the curve. And we'll show that sometimes parts of it will be negative, some parts of it will be positive. But all you need to know is what the antiderivative of f is. So to check that, you can take the derivative of capital F, and if it's equal to f of x, then you need to just basically calculate the antiderivative at the right endpoint minus the antiderivative evaluated at the left endpoint. And we use this notation, f of x, with a horizontal line, then a and b. This just means to plug in b and then plug in a and then subtract them. This is an amazing theorem. Now, understanding definite integrals, what it really means to take a definite integral. Let's take a function f of x as our first example. And suppose the entire curve that we're concerned about is above the x-axis from A to B. Then if we calculate the integral A to B of f of x dx, which would be equal to f of b minus f of a, that will equal the total area that you see shaded here with the lines. And you could just imagine have a plot of land that might go like this along a highway and want to calculate how many acres or how many square feet of area you have. If you could write an equation for this curve, you could calculate the area exactly. Now, you do need to understand that if for any function that could be positive or negative, that the integral from a to b, in this case, of f of x dx is going to equal the integral from a to, let's call this point C, of f of x dx plus the integral from C to D of f of x dx plus the integral from D to V of f of x dx. And that integral is going to be 8 because the area under this first bump is 8. But the area under the second bump, since it's negative, is going to be -9. And then this third bump will be 12. And this is equal to 11. So it's not equal to the total area, sum of the total area under the 3 bumps. This 9 takes away from the 8, and then the 12 adds back to it. So if you wanted to know the total area, you would have to take the absolute value of interval 1 plus the absolute value of interval 2 plus absolute value of interval 3. And of course, that total area, if that was land, would be 8 plus 9 plus 12. Equal 29. Now, let's talk about the second fundamental theorem of calculus. And it basically says if you take the derivative of the antiderivative, you'll get back your function. So, reading this, if f is a continuous function on a to b, then if you write capital F of x as the integral from a to x of f of t dt, then capital F of x is continuous on AB and it's differentiable on the open interval AB, and its derivative is f of x. That just says capital F prime of x is equal to f of x. And what that means, that to calculate the derivative of capital F of x, you just take x and put it everywhere you see a t. Now, in the second theorem, if the upper limit is not x, but g of x, then you have to use the chain rule. and substitute g of x everywhere you see a t. But then multiply by g prime of x. That's the chain rule. Another property of integrals, if you integrate from a to b of f of x dx, it's exactly equal to the negative of the integral from b to a of f of x dx. Now I'm going to basically reiterate another property of definite integrals. We've already, it's pretty much implied that this is so. Suppose you had a function y equal f of x, and you were looking at it from x equal a to x equal d, and you broke it up into three parts, and just think about a practical problem would be, suppose the curve here was a fence line, and the x-axis was a highway, and you had a fence going along this lower boundary, and then you planted corn and then cotton and red and then peanuts. And if you wanted to know the total acreage that you got for all three of your crops, it would be the integral from a to d of f of x dx, which would equal the integral from a to b of f of x dx. That would be your corn. The integral from b to c would be your cotton. And the integral from f of x from c to d would be your peanuts. In fact, I can remember when I was growing up in Lyons, Georgia, that I would grow peanuts like an acre or so, and then pull them up, and my mother would boil them. We'd have boiled peanuts. But anyway, this is visually pretty obvious what this property is of taking the total integral from a to d and breaking it up into pieces. Next, we're going to talk about and show some examples later about how to calculate indefinite integrals using substitution. This is when you might have a complicated looking integral. You can't obviously, not sure what the antiderivative is. So you don't know what the antiderivative is. However, in this particular example, if g prime of x is in the integral within the integral sign, or the integral symbol, then u equal g of x is a good choice. Substitution. Now, if you do use u equal g of x, then you'll calculate du dx equals g prime of x, and then cross multiply, and you get du equal g prime of x dx. Then substitute that in the interval above. And if you let u equal g of x, you'll be integrating the integral f of u du. And hopefully this f of u function will be simple. To integrate. So note and remember that a y substitution is u equal g of x if you see g prime of x appear in the integral. See the practice test and practice test video, and also the other problems that will be worked in this Zoom video. Another thing to remember, if you have a definite integral and you're using substitution and you need to calculate an actual number of the integral from a to b, and you're using substitution, you need to change the limits of integration using u equal g of x. In other words, you'll have to get an upper u equals g of b, where b is the upper x, and the lower u equal g of a, where a is the lower value of x. Now looking at some more concepts about calculating integrals, we've got two examples here. Over here, I have two functions, a u of x called the upper function, and an L of x I'd call the lower function. And if one is above the other for the entire interval from a to b, then you can see the shaded area would have an area of a, and the area a would equal the integral of the upper minus the lower. And that would give you the area that's shaded here. Now, in some cases, one function will not always be above the other one. And there you would have to break it up. So, for instance, suppose we have g of x given by this function and h of x given by this function. You can obviously see that between a and b, that g of x is above h of x. So to calculate this part, we go from a to b of g of x minus h of x dx. And to calculate this part, we go h of x minus g of x. That's the upper minus the lower. And so that would calculate the area of these two pieces. Now here's a simple problem of writing a summation notation for a sum of these numbers. And notice it's 9 plus 10 plus 11 plus 12 plus 13 plus 14. There are 6 terms. And you want to pick out which one of these summation notations equals that. Notice that for the first one, this does have 6 terms, so it's a candidate. Look at the last one, it's got 6 terms, so it's a candidate. Now this term, this one has only 5 terms. It's not going to be it. In addition, the first term that's calculated would be 18. So it's for sure not it. And this other one is going to alternate minus and plus. depending on what you put up in K. This only has 3 terms, so it's not going to be it. This one with 6 terms starting out at K equals 0, you're going to have 0 plus 1 plus 2 plus 3 plus 4 plus 5. That's not it. It's going to be the first one, which you could have seen in the first place. Putting in K equals 0, you get 9 for the first one. Then K equal 1, you get 10, 9 plus 10 plus 11 plus 12 plus 13 plus 14. So our answer is A. Now we're going to look at approximating the area under the curve. The first example is going to be using an upper sum. We're going to go from x equals 3 to x equals 7. Notice that the total length of this is 4. So delta x in this particular case is going to be 4 divided by 4, because we're going to use 4 rectangles equal 1. So the width of each rectangle is 1. And if we want to use an upper sum, we'll start with the top rectangle, which covers the entire curve between here and here. And so, and it's just going to be touching the curve at the upper end. So the height of this rectangle is going to be 49. And since this is 6, this one will be 36. The next one will be 25. And the next one will be 16. And since the width of each rectangle is 1, the area is going to be 16 plus 25 plus 36 plus 49 is equal to 126. And this will be an upper bound. Now let's look at doing a lower sum, which will be a lower bound. And we're still going to go from 3 to 7. The width of each rectangle is still going to be 1. But if we draw a rectangle here at the top so that the entire rectangle is underneath the curve, we would take the height of the rectangle to be f of 6, which will be 36. The height of the next largest rectangle will be 25, which is 5 squared. And the height of the next to the smallest rectangle would be 16. And then the last rectangle would be a height of 9. So the area is equal to 9 plus 16 plus 25 plus 36 equal 86. So now from both of these problems, we know the true area is more than 86 and less than 126. And using the fundamental theorem of calculus, we can calculate the true area is equal to the integral from 3 to 7 of x squared dx equals x cubed over 3 evaluated between 3 and 7. And this is going to be equal to 7 cubed over 3 minus 3 cubed over 3. And you do the math and you will get 105.33. So we know that the true area is 105.33. Now the handout I've given you shows you how to do all of this in detail. Now we're asked to write this sum without sigma notation and evaluate it. Well, let's plug in k equal 1 and we get minus 1 squared cosine of 4 pi. Plug in k equal 2, we get minus 1 cubed cosine of 8 pi. And then for k equal 3, minus 1 to the 4th power cosine of 12 pi. So that would be, this would be 1, so this would be cosine of 4 pi minus cosine of 8 pi plus cosine of 12 pi. And notice cosine of 4 pi is 1. Cosine of 8 pi is 1 too. So we're going to have 1 minus 1 plus 1 equal 1 is the answer. Now we're given a couple of definite integrals, and we want to find another definite integral. We're given f of x dx integrated from 5 to 9 is equal to minus 2. G of x integrated from 5 to 9 is equal to 7. And then we want to find the integral of f of x minus 2g of x from 5 to 9. So the integral from 5 to 9 of f of x minus 2g of x dx is going to equal, first, the integral from 5 to 9 of f of x dx and plus the integral from 5 to 9 of minus 2g of x dx. Now I could have skipped this step and just written integral from 5 to 9 f of x dx minus 2 integral from 5 to 9 g of x dx. And notice that this is given as minus 2. This integral is given as 7. So this is going to be minus 2 minus 14 equal minus 16. Just check your work carefully. Now we have a function f, and we have one integral from minus 2 to plus 2 f of z dz is 0. Minus 2 to 7 of f of z dz is 6. And we want to find the integral from 7 to 2 of f of z dz. Let's notice that the integral from -2 to 7, which is a full length here of f of z dz, is equal to the integral from -2 to +2 of f of z dz plus the integral from 2 to 7 of f of z dz. And now looking at the parts we know from -2 to 7 is 6. From -2 to +2 is given as 0. Plus the integral from 2 to 7 of f of z dz. So now we know that this has got to be 6. In other words, the integral from 2 to 7 of f of z dz must be equal to 6. So using the other property we know of integrals, the integral from 7 to 2 is going to be the negative of that. So that's the answer to this one. Now let's evaluate the integral here with some real functions. The antiderivative of z is z squared over 2. Antiderivative of minus the square root of 6 is minus the square root of 6z. And we want to evaluate that between 2 and the square root of 6. And so that's going to be the square root of 6 squared over 2 minus the square root of 6 times the square root of 6 minus, plugging in 2, we get 2 squared over 2 minus 2 square roots of 6. And this becomes, this is 3, this is 6, and this is 2. Then we have plus 2 square roots of 6. So this is equal to minus 5 plus 2 square roots of 6. And that is this answer right here. Now we're given two functions, f and g, and we're given various pieces of information. Integral from 2 to 4 of f of x is minus 4, from 2 to 7 of f of x is minus 5, and the integral from 2 to 7 of g of x is minus 4. And it says use this information to complete parts A through F. Now the first was very simple. It's just an integral from 4 to 4, and that's an interval that's of 0 width, and so that is going to be 0. And you can actually prove that by saying the antiderivative of little f of x is capital F of x, and evaluate that at 4, capital F of 4 minus capital F of 4 is 0. But it just stands to reason that if you have an interval that's 0, the area under the curve is going to be 0. Now, the next one integral from 7 to 2 of g of x dx is, we're going to get that first of all, we're given that the integral from 2 to 7 of g of x dx is equal to minus 4, so we'll reverse it and go 7 to 2 of g of x dx is going to be plus 4. So that's simple enough. C, we want to find 9g of x dx, and 9g of x dx from 2 to 7, we're going to just multiply it by 9 and we get minus 36. Number D, we want to calculate the integral from 4 to 7 of f of x dx. To do that, we have to note that the integral from 2 to 4 of f of x dx plus the integral from 4 to 7 of f of x dx is equal to the integral from 2 to 7 of f of x dx. Now we're given that this integral is minus 4. And this integral from 4 to 7, which is what we want to find, and then the integral from 2 to 7 is equal to minus 5. So the integral from 4 to 7 of f of x dx is going to be minus 5 plus 4 equal minus 1. So the answer to D is minus 1. And finally, we want to do E. We want the integral from g of x minus f of x d of x from 2 to 7. Well, this is going to equal the integral from 2 to 7 of g of x dx minus the integral from 2 to 7 of f of x dx. From 2 to 7 of g of x dx is minus 4. From 2 to 7 of f of x dx is minus 5. So this is going to be minus 4 minus 5 equal 1. So that is 1. And then finally, this last one is going to be the integral from 2 to 7 of 2g of x minus f of x, minus the integral f of x dx from 2 to 7. So 2 to 7 g of x is minus 4. So 2 times that is going to be minus 8. And then the integral of f of x dx from 2 to 7 is minus 5. And so we get minus 8 plus 5 equal minus 3. So the answer is minus 3 for this last one. Now let's evaluate another definite interval from 2 to 4. We're going to get the antiderivative as x cubed minus x to the 5th over 30. And we want to evaluate that at 2 and 4. So plugging in 4, we get 4 cubed minus 4 to the 5th over 30 minus, plugging in 2 cubed minus 2 to the 5th over 30. And this equals 64. 4 to the 5th happens to be 1024. 1024 over 30. 2 cubed is 8, so it's minus 8. And then we have minus 2 to the 5th, which is 32 over 30. And this is 56 minus 92 over 30. Simplifying this, you can get it to be 344 over 15. And we want to evaluate this integral. The antiderivative of x plus 3 to the 3rd power will be x plus 3 to the 4th power over 4, integrating between 0 and 4. We get, plugging in 4, we get 7 to the 4th over 4. Plugging in 3, we get, plugging in 0, we get 3 to the 4th over 4, which is 2401 divided by 4 minus 81 divided by 4. And you get this to be 580 after you simplify it. Evaluate the integral here, e to the 2x from 0 to ln of 5. We first get the antiderivative e to the 2x, which would be e to the 2x over 2. It's not just e to the 2x, you have to remember the chain rule and also take the derivative of e to the 2x over 2 and show that it equals e to the 2x. So you then need to evaluate that between 0 and ln of 5. And you get e to the 2 ln of 5 divided by 2 minus e to the 0 over 2. And this is equal to e to the ln of 25 divided by 2. Notice that 2 ln of 5 equals ln of 5 squared equal ln of 25. Then e to the 0 is 1, so we have e to the ln of 25 over 2 minus a half. E to the ln of 25 is just 25 because e to the ln of anything is equal to anything. That comes from college algebra. And so your final answer is 24 over 2 equal 12. Another integral, the antiderivative 23 sine of x would be minus 23 cosine of x between 0 and pi over 2. And that equals minus 23 cosine of pi over 2. Minus 23 cosine of 0 Cosine of pi over 2 happens to be 0. Cosine of 0 is 1, so this is going to be equal to plus 23. Now we're going to look at the second fundamental theorem of calculus and apply it. Notice that one thing is missing here is dt. We got y equals the integral from 1 to x of secant of t square root of sine of t plus t to the fourth. And we want to find the derivative, so dy dx equal y prime. Remember, we want, if it's just plain old x up here, we plug in x everywhere we see a t. And y prime is equal to secant of x times the square root of sine of x plus x to the fourth. Now we have another one where we want to take the derivative of an integral, except the upper limit is not plain old x, it's a square root of x, it's a function. So what we need to do is plug the square root of x everywhere we see a t, but not stop there. And when we do that, we get 7 square root of x times cosine of the square root of x cubed. But then we need to multiply by d dx of the square root of x. So this is the 7 square root of x cosine of x cubed. Notice that d dx of the square root of x, we have x to the 1/2, and this derivative is going to be 1/2 x to the minus 1/2, which would be 1 over 2 square roots of x. So this is 1 over 2 square roots of x. And notice we have some simplification here. The square root of x is canceled, and we get 7/2 cosine of x cubed. Okay, in this problem, we want to find the area of the region between the curve and the x-axis. Notice, looking at the curve, we want to calculate this area plus this area. And since this integral from 3 to 5 would be negative, we need to take really the upper curve, which would be the x-axis, minus the lower curve. So let's look at how we would do this. We would calculate the integral from 0 to 3 of the upper, which is minus x squared plus 9, minus the lower, which is 0. That would be this line, dx, plus the integral from 3 to 5 of the upper, which would be 0, minus the lower, which is minus x squared plus 9 dx. And to simplify this a little bit before we integrate, it'd be between 0 and 3. Minus x squared plus 9 dx plus the integral from 3 to 5 of x squared minus 9 dx. And now we'll integrate, and we'll get minus x cubed over 3 plus 9x. We'll evaluate between 0 and 3. And plus the integral of x cubed minus 9 is x squared minus 9 is x cubed over 3 minus 9x. And we'll evaluate that between 3 and 5. And now, plugging in 3, we get minus 27 thirds plus 27. Then plugging in 0, we get 0. Then we get plus 5 to the third power, which is 125 thirds, minus 45, minus, plugging in 3, we get 27 thirds, minus 27. And this is equal to minus 9 plus 27 plus 125 thirds minus 45 minus 9 plus 27. And if you simplify this, you get minus 9 plus 125 thirds, which is equal to 98 thirds. And that is the area of both of these pieces here. Next one is to find the area under this curve. So we would want to calculate the definite integral from minus pi to plus pi of cosine of x plus 1 dx. The antiderivative of cosine of x is sine of x. Antiderivative of 1 is x. And calculate with minus pi and plus pi. We get sine of pi plus pi, plugging in pi, and minus what we get when we plug in minus pi, which is sine of minus pi minus pi. Sine of pi is 0. Sine of minus pi is 0. So we get 2 pi is the area under this curve. Now we want to solve an initial value problem. We're given dy dx is this function. I don't obviously see what the antiderivative is, so we're going to have to probably use a substitution. We know that y would be the integral of x 3 plus x squared dx. And notice that if we let u equal 3 plus x squared, the derivative is going to be 2x, which is almost exactly equal to x. It's just off by a factor of 2. So we're going to let u equal 3 plus x squared. Du dx is equal to 2x. So cross multiplying, we get 2x dx equal to u, and x dx is equal to du over 2. So now we can see that x dx here would be du over 2. And then the 3 plus x squared would be u. So y is going to be equal to the integral of u squared over 2 du. Now see, using this substitution, we got a much easier function to integrate. So y is going to be equal to u cubed over 6. That's the antiderivative of u squared over 2 plus a constant. And now u is 3 plus x squared, so this becomes 3 plus x squared cubed over 6 plus a constant. So what is the constant? Y at 0 is given is equal to 0. So plugging in x equals 0, we get 3 to the third power is 27 over 6 plus c. That is equal to 0, so c is equal to minus 27/6, which is minus 9/2. So now y is equal to 3 plus x squared to the third power over 6 minus 9/2. And there is the answer right here. Now we have another indefinite integral that we want to calculate, and we'll need to use substitution also. Here we have 3 minus sine of t over 5 squared times cosine of t over 5 dt. And you can see the derivative of sine is cosine, so picking u equal 3 minus sine of t over 5 is a good choice. Du dt is going to be ddt of 3 is 0, of course, but this is going to be minus 1/5 cosine of t over 5. So du is equal to minus cosine of t over 5 divided by 5 dt. And that means that cosine of t over 5 dt is going to be equal to minus 5 du. That all comes from this. Solve for cosine of t over 5 dt, and it will be minus 5 du. So now this will be minus 5 du. 3 minus sine of t over 5 is u. So now the integral of 3 minus sine of t over 5 squared times cosine of 1 cosine of t over 5 dt is going to be equal to the integral of minus 5 u squared du. And this is going to be minus 5 u cubed over 3 plus a constant. And remembering what u is, this will be minus 5 of 3 minus sine of t over 5 cubed divided by 3 plus a constant. So here is the answer. Now we have another one. We're even given the substitution. If we're going to use u equal 2x squared, notice du dx is 4x. So we see x sitting here, so we're only off by a factor of 4. So let's do the substitution. Du dx equal 4x. Cross multiply, we get du equal 4x dx. And that x dx then is du over 4. So let me not go through all that. X dx here is du over 4. 2x squared is u. So this integral of x cosine of 2x squared dx is going to equal the integral of cosine of u du divided by 4. And calculating the antiderivative, that would be sine of u over 4 plus a constant. And remembering what u is, it's going to be sine of 2x squared over 4 plus a constant. Now we've got a definite integral, which we're going to have to use a substitution for. But it looks like this substitution is going to be pretty straightforward. Look at what's under the radical. It's 9 plus 5r squared. The derivative of that is 10r, which is sitting right here on top. So that's good news. Let's let u equal 9 plus 5r squared. Du dr is equal to 10r. So du is equal to 10r dr. And notice that here we have 10r dr. That's going to be our du. And 9 plus 5r squared is going to be u. So this integral from 0 to 1, 10r dr over the square root of 9 plus 5r squared is going to equal an integral. We're going to get the upper and lower in a second. But we're going to have du over the square root of u du. And let's get the lower. The upper u is going to be equal to 9 plus plugging in the upper x, plugging in 1. We're going to get 9 plus 5 equal 14. And the lower u is going to be 9 plus 0, plugging in 0 is 9. So the integral is going to be from 9 to 14. So to do this integral, we're going to do the antiderivative of u to the minus 1/2 du, which is equal to u to the 1/2 over 1/2 from 9 to 14. And notice this is 2 square roots of u from 9 to 14, which is equal to 2 plugging into 14, 2 square roots of 14 minus 2 square roots of 9, which is 2 square roots of 14. The square root of 9 is 3, so this is going to be minus 6. So the answer is A here. Now we want to find the area of the shaded region. We've got the upper curve is minus x to the fourth. And notice the lower curve is x to the fourth minus 32. So we will simply take the integral from minus 2 to plus 2 of the upper, which is minus x to the fourth, minus the lower curve, which is x to the fourth minus 32 dx. And this is equal to the integral from minus 2 to plus 2. We're going to have minus 32, which will be a plus 32. I'll lead with a positive term, minus 2x to the fourth dx. And this is going to be 32x minus 2x to the fifth over 5. And we want to calculate that between minus 2 and plus 2. So plugging in 2, we get 64 minus 2 times 2 to the fifth is going to be 64 fifths minus, plugging in minus 2, we get minus 64. And then plugging in minus 2 here, we get plus 64 fifths. And this is going to be 128 minus 128 fifths, which is 512 fifths, which is the area between these two curves. So the last problem is very simple if you remember what an even and an odd function looks like. Suppose that the integral of f of x dx between 0 and 3 is equal to 9, and you wanted to find the integral from minus 3 to 0 if f is odd. Now, we're told that the integral from 0 to 3 is 9. So the area under this curve is 9. If it were an even function, the left and the right would be mirror images of one another. And this area, of course, is given as 9. And so the other side would be 9. And so if it were an even function between minus 3 and 0 would be 9. But it's an odd function. Since it's an odd function, it'll look like this. The left-hand side would be the negative, the right-hand side. And so its area would be minus 9. And that is the last problem.